So we're going to continue on now, and we're going to look at fundamental problem 3. A particle travels along a straight line with a velocity of 4t minus 3t squared, which is in meters per second when time is in seconds, just by looking at the equation that they give us for the velocity and recalling that the acceleration is equal to the derivative of the velocity with respect to time. You can tell from looking at this that the acceleration is not constant, which means we can't use the equations here, which are for constant acceleration. Okay, so we want to determine the position of the particle when t is equal to 4 seconds. So I'm going to write that as find the position s when t is equal to 4 seconds. And then they're telling me that the position is equal to 0 when time is equal to 0. So the position when t is equal to 0 is equal to 0. That's going to give me my lower limits of integration. I'm looking for the position. I have the velocity as a function of time. So I'm going to stick with using the 3 equations that I have here. Okay, so take a look at these 3 equations. I could, let's do this today. Okay, so if I take equation 1 and bring the dt over to the other side, then I have ds is equal to v dt. Take equation 2 and bring the dt over to the other side, and you have dv is equal to a dt. And now these have a form which is similar to equation 12-3, which says a ds is equal to v dv. Okay, so this was equation 12-1, this was equation 12-2, this was equation 12-3. Okay, now we have velocity as a function of time. We're looking for position. So this equation doesn't have time in it, okay, so we're not going to use equation 3. And this equation has acceleration in it, which we are not looking for, and we're not given any information about. So we're going to use equation 1 here because we have velocity as a function of time and we're looking for position. So this is going to work out really nicely. We're going to integrate. We're integrating with respect to position here. So this is going to be from S1 to S2 as we integrate with respect to time on the other side. So that's from time 1 to time 2. So I'm going to say my lower limits of integration are when time is equal to 0, and I have to have the corresponding position on the other side, but when time is equal to 0, I know that position is equal to 0. Okay, so I can do this because the lower limit of integration on this side, which is time 1, that's 0, when position 1 is also equal to 0. That's just a ds. I'm looking for the position when time is equal to 4 seconds. I'm just going to call that S. Okay, that's my final position when time is equal to 4 seconds. At this position S, my upper limit of integration for time is going to be 4 seconds. Then I have to put in the velocity equation that I have, so that's 4t minus 3t squared, integrating with respect to t. Okay, so on the left-hand side, when I integrate, I'm integrating with respect to s. So when I integrate, I just get s. I plug in my limits of integration. You can say s minus 0. You can skip writing the minus 0 if you want to. This is similar to what we did in Physics 261. If you really wanted to leave the upper limit of integration as s2, you could do that, or you could call it something else, but I like just calling it s. Okay, now, on the other side, we have velocity as a function of time, so we can integrate with respect to time. So for t, when I integrate that with respect to time, I would get 4t squared divided by 2, minus when I integrate 3t squared with respect to time, I'd get 3t cubed divided by 3, and then I plug in my limits of integration, which are from 0 to 4 seconds. I think I'm going to leave the seconds out there and just plug in the 4 because I have the s on the other side too. Okay, so s is equal to 4 divided by 2 is just 2, so this is 2 times 4 squared minus 3 over 3 is 1, and then I plug in the 4 here, so that's minus 4 cubed. And then when I plug in the lower limit of integration, this term is going to be 0, and this term is going to be 0, so that's just minus 0, minus 0. So again, you could skip writing that if you want to. Okay, and then when we plug in numbers here, we're going to get s, well, this is equal to minus 32. So s, when t is equal to 4 seconds, is equal to negative 32. And the velocity would be in meters per second. I left out the unit for the time there when I plugged things in, but if this is the position, this should be in meters. Okay, and that is fundamental problem 3. And let's go ahead and do fundamental problem 4. Also, so a particle travels along a straight line with a speed of 0.5 times t cubed minus 8t meters per second, where time is in seconds. Determine the acceleration of the particle. Oops. Find the acceleration of the particle when t is equal to 2 seconds. Okay, so I'm looking for the acceleration, and I have the velocity as a function of time. So, well, I have my 3 equations here, but actually for this one, I probably want to use the equation that was given in the form it was given in the equation sheet. Let's just take a look at these 3 and see what we would get. If we look at equation 1, we're not interested in the position, so let's move on. Equation 2 has velocity, acceleration, and time in it. That looks promising. Equation 3 has position in it and no time. Okay, so we're going to say equation 2 is what we want to use, but the way it's written here, we'd be integrating acceleration. But we already have the velocity as a function of time, so if we go back to what we have here, acceleration is the derivative of the velocity with respect to time. dv dt. Okay, so I have my velocity as a function of time, so I'm going to go ahead and take the derivative there. So the derivative of 0.5t cubed minus 8t, that would give me this would be 1.5 t squared minus 8. This is the acceleration as a function of time. But I want the acceleration when time is equal to 2 seconds, so then I'm going to go ahead and evaluate this. Is equal to 1.5 t squared minus 8, evaluated when t is equal to 2 seconds, and that gives me 1.5 times 2 squared, which is 1.5 times 4, minus 8, that's minus 2. This is acceleration, which has units of meters per second. And that concludes fundamental problem 4. Okay, I gave you a little more detail today than I ordinarily would because these are the first problems that we're looking at. So this was hopefully a lot of review, and that concludes fundamental problem 4.